In this lecture, we're going to look at an example of how sample size can affect the variability measures, and we're going to use birth weights of babies as an indication of how the sample size obtained from a population can affect our variability measures. And so in this example here, we're going to take a number of samples. In each sample, we have 10 babies within which the birth weight was measured. And we then take another sample, and we continue until we take thousands of samples. And once we do that, along the bottom distribution, what we see here is that we are examining the distribution of the averages of each sample, not the individual babies per se. And so recall that when we have a frequency distribution, our key outcome variable, in this case birth weight, is placed along the x-axis, where mu represents the population average or the population mean. And this is because we have a number of samples here, this is going to be an estimate of the population mean. Now, the peak of this frequency distribution, as you can see here in this middle bar, indicates that at approximately 800, we'll just go with 800, we see that most samples, 800, the highest number of samples, had a sample mean equal to the population mean. And so we have something that looks like a normal distribution. And so the dotted line here, the dotted line is our overlay of the normal distribution on top of the actual real data from these samples. Another way that is not as commonly used to represent a frequency distribution is what's called the frequency polygon, and that's just illustrating two different ways. However, the histogram is the most common way. Now, what we see here in this box is that the n equals the sample size of 10 babies in each sample. And once again, what we're measuring here are the averages of each of the samples. And we took thousands upon thousands of these samples. And this is obscured by this arrow here, but this symbol here is the sample standard error of the mean, and that gives us a value of 9.5. And the way we found that is we just simply took the standard deviation of a given sample. So if we randomly picked one of these samples of 10 babies, we might find the sample standard deviation to be 30, for example. And when we divide that by the square root of the sample size, which in this case is 10, we get a value of 9.5 pounds. And that is what we call the standard error of the mean. And we use the symbol of S, which is the same as the standard deviation, but we use the subscript X bar to indicate the standard error of the mean. To illustrate the effect of sample size, here we see a similar or actually the exact same experiment where we wanted to measure birth weights, except that each sample, instead of consisting of 10 babies, now consists of 50 babies. And so what this does, by increasing the sample size, it decreases the overall number of samples. So as we see here, with our sample size of 50, because if we pick one sample randomly, and once again, let's use the same standard deviation of 30, divide that by the sample size, or rather the square root of the sample size, which is 50, we now have a lower standard error of the mean at 4.2 pounds. And so this becomes an indicator of the variability of the samples around the population mean. If we were just interested in the sample statistics, then we would just take a look at the sample standard deviation. And so in a similar manner, what we see here, we see an almost perfectly normal distribution in the histogram overlaid onto a more leptokurtic normal distribution. But this tells us that more samples, approximately actually just slightly greater than 1,400, had a sample mean equal to the population mean. And by taking a larger sample size, it reduces the variability. And so more of the samples of 50 babies that we're taking, each sample had a mean that was closer to the population mean. And although we don't have the actual data for the population, we make this statement through what's called the central limit theorem. And this is a theory in which the sampling distribution of the means, if taken enough times, will always form an approximately normal distribution, and that allows us to carry out a range of inferential statistical techniques. The central limit theorem also states that the distribution of the means will have a mean equal to the population mean. So the mu represents the mean of the population, and mu subscript x bar are the averages of the sample averages. And if we take a large enough number of those, then our mean will equal the population mean. And the central limit theorem also states that the standard deviation will be mathematically related. That would be the population standard deviation, will be related to the standard deviation of the raw score population. So the standard deviation obtained from our samples, in theory, will equal that if we take the population individually. And what we see here at the bottom of the slide is a demonstration of the population level, where we have the population standard error of the mean is going to be equal to the population standard deviation divided by uppercase n, in this case, the population size. So this ends this brief video on the effect of sample size on standard error measures.